Welcome to Life with David. I'm David, and today, by request, we have a very special crossover event. The PIO Chronicles meets Bare Metal Adventures. This time, I'll demonstrate how to invoke Programmable Input Output on the Pico using assembly language, but without using the SDK. As President Kennedy proclaimed over 60 years ago,
"We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard."
Of course, the other things in his speech refer to our topic today. This exercise is not something you would do in everyday programming, but it's really helpful to improve both your assembly language and PIO skills. So why don't you join me as we really get into the weeds and do some assembly language programming of the RP2040 PIO. For a PIO refresher, you can review my PIO series, the PIO Chronicles. In this video, we'll be using a PIO LED blink program that was originally programmed in C in episode 7. I'll put a link in the description below. I'll also be using assembly language without using the SDK. For more information, please see chapters 4 and 5 of Bare Metal Adventures. We'll be using the phase lock loop clock program that was originally presented as Demo 5 of Chapter 5. I'll put a link in the description below. As always, the RP2040 datasheet will be our guide for this journey. As you can see from Figure 4, the PIO is a special high-bandwidth peripheral that shares a port on the advanced high-performance bus of the RP2040. The PIO is programmed using 9 instructions: jump, wait, in, out, push, pull, move, interrupt request, and set. The encoding for these 16-bit instructions are shown in Figure 365. Each PIO block can access up to 32 instructions in the PIO memory. This program memory is shared among 4 state machines. To implement PIO, we have to set several parameters. Let's look at example 1 of episode 7, which blinks a GPIO output. Inside the C program, we specify which PIO block, GPIO pin, and the state machine clock frequency we want to use. The PIO program is loaded into memory and a state machine is claimed. Then, inside the PIO file, the parameters are converted into a configuration for the PIO using the SDK. Starting with the default configuration, the GPIO pins for in, out, set, and side set are allocated and configured. The clock divisor to determine the state machine clock frequency is calculated and loaded. The state machine is then started and enabled. The result is an LED that blinks about 2 times per second. Now let's make this happen without the SDK and the PIO assembler. Each PIO block is configured using 80 registers. These are detailed in section 3.7 of the RP2040 datasheet. 32 registers are dedicated to storing the PIO program. 4 registers are for the PIO block, 7 are for interrupts, and the rest are dedicated to the state machines. Luckily, we only need to use a few registers to make our LED blink. Let's write an assembly program to configure these registers. As mentioned earlier, I'll start with a previous program that initialized the phase lock loop clock to generate a system clock of 125 MHz. This program starts the crystal oscillator, switches to the crystal oscillator, sets up the crystal oscillator for outputting, starts up the phase lock loop, enables the phase locked loop, releases the reset for IO bank 0, and routes the crystal oscillator to GPIO 21. Now let's add PIO functionality. PIO is a peripheral that is not critical to boot the processor in the RP2040. That means it's not reset by the power on reset or the power on state machine, similar to IO bank 0 or the phase locked loops. The subsystem reset controller holds all these non-critical peripherals in reset until our software releases them. So the first thing we need to do is to release the reset for PIO and then check if the reset is complete. The reset sequence is identical to what we did for IO bank 0, we just use a different bit. As we can see from section 2.14.3, PIO 0 and PIO 1 use bits 10 and 11 respectively. Since we'll run our program on PIO 0, I'll use bit 10. First, I'll load register 0 with the base address of the atomic register for clearing the subsystem reset. As a reminder, an atomic register allows setting or clearing individual bits of a register without having to do the whole read, modify, write dance. Many peripherals have these registers, and they're located at offsets from the normal base address as specified in section 2.1.2 of the RP2040 datasheet. Then I'll set bit 10 of register 1, which is the select for PIO 0. Next, I'll store register 1 in the atomic clear register. Since it takes a while for the PIO reset to clear, I'll enter a loop where I read in the reset done register, isolate bit 10 and check if it's 0. If bit 10 is still 0, PIO 0 is still in reset, so I'll check it again. This continues until bit 10 is set and PIO 0 is out of reset. After PIO is out of reset, it's time to load the PIO program into the PIO 0 block memory. The PIO program is very simple. First, the set command turns on the base set pin. This instruction includes a 31 clock cycle delay for a total of 32 state machine clock cycles. Next, there are 7 no-op pseudo instructions. A no-op simply assembles to move register Y to register Y. Each no-op also includes an additional 31 state machine clock cycle delay. Then there is a set command that turns off the base set pin, also taking 32 state machine clock cycles. This is followed by 6 additional no-op commands, again taking 32 machine clock cycles each. Finally, there's a jump taking 32 state machine clock cycles to return the PIO program counter to the beginning of the PIO program. Normally, the SDK chooses where to locate the PIO program in memory. However, since we're not using the SDK, we get to choose where we want it to be. I'll choose to start the PIO program at location 0. Now let's convert these PIO instructions to machine code. I'll refer to section 3.4 of the RP2040 datasheet. As you can see, the PIO instructions are 16 bits long. The 3 most significant bits are the opcode for the instruction. Bits 8 through 12 specify the number of clock cycles to delay, the output of the side set pins, or both. The function of bits 0 through 7 depend on the individual instruction. Let's start with the first PIO instruction, the set command. I put together this little form to help me keep all the bits and bytes in order. Since the PIO instructions are only 16 bits long, the first thing I do is load the 16 most significant bits with 0, even though it really doesn't matter. Then, in section 3.4.10, we see that the set opcode has all ones in the 3 most significant bits, so I add them in bits 13 through 15. We want to add 31 delay cycles to the instruction so we have a chance to see it blink. So we'll fill bits 8 through 12 with the binary representation of 31, or 5 ones. The destination is in bits 5 through 7. Since we want to send it to the set pins, we'll fill this section with 0, 0, 0. Bits 0 through 4 contain the code we want to send to the set pins. Since we want to turn on the base set pin, we'll set the least significant bit. Now we can use the form to encode the instruction. The resulting word is 0000FF01 hex. The next 7 instructions are no-ops, which actually is encoded as move Y to Y. In section 3.4.8, we see bits 13 through 15 are 1, 0, 1. Since we again want 32 additional delay cycles, we will fill bits 8 through 12 with all ones. Both the source and the destination are the white scratch register, which is identified as 0, 1, 0. So we'll insert that number into bits 0 through 12 and 5 through 7. Finally, we don't want to perform any special operation, so we'll enter 0, 0 into bits 3 and 4. The resulting word is 0000 BF42 hex. The next instruction uses the set command to clear the base set pin. It encodes just like the first set instruction, except the last bit is 0 instead of 1. The resulting word is 0000FF00 hex. Then 6 more no-ops precede a jump instruction which points the PIO program counter back to the beginning of our blinking program, which is location 0. Referring to section 3.4.2, we see that bits 13 through 15 are 000 and bits 8 through 12 are 1111 for 31 additional clock cycles. Since we always want to perform the jump, we'll enter 000 into bits 5 through 7. Finally, we want to jump to location 0, so we'll enter 00000 into bits 0 through 4. The resulting word is 00001F00 hex. I'll locate the PIO program at the end of the assembly program after the label PIO Prog. I didn't want to try too many new things at once, so I designated each instruction as a 32-bit word, but I'm sure I could have listed them as half words just as easily. Per section 3.7, the PIO instruction memory for PIO Block 0 is located starting at register 502-00048 hex. In table 379, we see that each PIO instruction resides in bits 0 through 15, with bits 16 through 31 not being used. This is the same format as our program, so we'll do a straight one-to-one transfer into the PIO registers. I'll load the program by first loading the pointer to the starting address of our PIO program, PIO Prog, into register 0. Then I'll load the first PIO instruction register location, PIO Prog Base, into register 1. Since I want the PIO program to start at the beginning of the PIO program memory, I'll assign 502-00048 hex to that constant. I could have added an offset at this point if I wanted our program to start at some other location in PIO memory. Then I'll load the number of instruction words I want to transfer into register 2. Now I'll enter a copy loop where I load the first word of the PIO program into register 3 and then store it in the first PIO 0 instruction register. Then I'll increment both the program listing pointer and the PIO instruction memory pointer by 4 bytes. Next, I'll insert a single blink of the onboard LED so I can watch the progress of the program. Then I'll decrement register 2, which holds the remaining number of words in the PIO program. As long as there's still words to transfer, the program will branch back to the copy loop. After the PIO program has been completely transferred, I'll set up GPIO4 as the base set pin which our PIO program will control. Since I've decided to use state machine 0 to run our PIO program, I'll set the base set pin using the state machine 0 pin control register located at 502-000 DC hex. As you can see from section 3.7, this register allows us to configure the in, out, set, and side set pins that will be used by state machine 0. There are identical registers for each of the other 7 state machines. Let me set up the configuration word for our program. Since I want the maximum number of delay cycles and I don't need any side set pins, I'll load 000 into side set count, bits 29 through 31. I want 1 set pin, so I'll enter 1 into set pins count, pins 26 through 28. I don't need any out pins, so I'll set bits 20 through 25 to 0. I'll set the base for the in, out, and side set pins to 0, although they could be any value. Bits 0 through 4 and 10 through 19 will be set to 0. That leaves a set pin base. Since I want to use GPIO04, I'll load 04 hex which is 00100 binary into bits 5 through 9. The resulting configuration word is 04000080 hex, which I'll assign to the SM0 pin control. I load the pin control register by first loading a secondary base address of 502.00080 hex into register 0. Note that I can't use the actual PIO 0 base address of 502.00000 hex, since the ARM thumb commands only allow a register immediate offset of 0 through 124 decimal. The pin control register offset from the base address is DC hex, which is 220 decimal, which means that the base address must be closer. Then I load our state machine 0 pin control configuration word into register 1. Finally, I store register 1 into the state machine 0 pin control register located at 502.000 DC hex. I've just told state machine 0 to use GPIO 4 as the base set pin. However, to finish the configuration, I have to tell GPIO 4 to expect commands from the PIO. Similar to how I set up the onboard LED, I'll refer to section 1.4.3. I'll assign function 6 for PIO 0 to GPIO 4 using the GPIO 4 control register located at 40014.024 hex. Let's refer to section 2.19.6.1 for more info on this register. I want to enable GPIO 4 as an output and then drive the output using the peripheral selected by the function, which is function 6 for PIO 0 in this case. I'll load the control register address for GPIO 4 into register 0 and then load 11 binary into register 1. We'll shift it over 12 bits and then add 6 for the function number. Finally, we'll store register 1 into the GPIO 4 control register. Okay, we got the output set up. Now we have to set the state machine clock frequency. Refer to section 3.7, state machine 0 clock divisor register located at an offset of C8 hex. As PIO comes out of reset, all the state machines run at the main system clock frequency. We can slow the individual state machine clock frequency down by using integer and fractional divisors in this register. Since I want a really slow clock frequency so I can see the blinking, I choose a large integer divisor of FFFF hex, which I load into bits 16 through 31. I want the clock to be jitter-free, so I'll use 0 as the integer divider. The resulting configuration word is FFFF0000 hex, which I'll assign to the constant SM0 clock divider. This section of code stores the configuration into the state machine 0 clock divisor register. Now we have to tell the state machine where to find the PIO program. Refer to the state machine 0 execution settings register located at an offset of CC hex. There are a lot of execution parameters we could set here. However, the only ones we're interested in today is the wrap top and wrap bottom. The wrap bottom is the start of the PIO program for this state machine and is equivalent to the wrap target. Since we choose to start the program at location 0, this parameter will be set to 0. The wrap top can be set to the end of the program, which will replace a jump command. Since I'm using the jump statement, I'll just set this parameter to 1F hex, or the top of the PIO program memory. The resulting configuration word is 000-1F000 hex, which I'll assign to the variable SM0 exec control. This section of code stores the execution configuration for state machine 0. Note that this is how the register comes out of reset, so I really didn't need to do anything, but I included it for clarity. See episode 4 of the PIO Chronicles for more information on wrap and wrap target. I'll put a link in the description below. Now we need to restart the state machine with all these modified configurations. Refer to the PIO control register at an offset of 0. First, I'll set bit 4 and store in the PIO control register to restart state machine 0. Then I'll shift the register left 4 bits so that bit 8 is set and store that in the PIO control register. This restarts the clock for state machine 0. Now I need to force an instruction into the state machine to force it to jump to the beginning of the PIO program. Refer to the state machine 0 instruction register located at an offset of D8 hex. The opcode for an unconditional jump to the PIO memory location 0 with no extra delays just happens to be 0000 hex, so I'll store that value into the state machine instruction register. For more information on forced instructions, please see episodes 10 and 11 of the PIO Chronicles. I'll put links in the description below. Finally, we need to enable state machine 0 to get everything running. Back to the PIO control register at an offset of 0, I'll set bit 0 and then store it in the control register. Now that the state machine is running, I'll just kill time with the main core by blinking the onboard LED located at GPIO 25. Let's try it out. I'll use the same process for compiling, linking, and creating the download file as I did in chapters 4 and 5 of Bare Metal Adventures. I'll put links in the description below. First, I'll save the program and then use make clean to delete the previously generated files. Then I'll run make all to compile the assembly program. Using make link links the second stage bootloader and the vector table to the assembly program. Make UF2 generates the UF2 file that will be loaded into the RP2040. Finally, this obj dump statement will create a disassembled version of the output so we can use it for debugging. Let's copy the UF2 file into the RP2040. We watch as the onboard LED blinks while the PIO program is being transferred into the PIO instruction registers. Then the PIO program is configured and started, and the LED connected to GPIO 4 starts blinking. Success! Thanks for joining me today. This time, we invoke the RP2040 PIO functions using assembly language, but without the SDK. Although I wouldn't do this for most PIO applications, there's something comforting about knowing how the SDK actually configures the PIO. I also learned a little bit more about the capabilities of PIO. Next time, I'll dive a little deeper into bare metal programming the RP2040, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!